And the first talk we have by Florent Benaych-Georges, cross-covariance matrices estimation. Please, the floor is yours.
So first I would like to thank the organizers for inviting me to speak here at this conference and discovering this nice city. So I will speak of RIE. RIE means Rotationally Invariant Estimator for cross-covariance matrices. It's a joint work with Jean-Philippe Bouchot and Mark Potters. So let me start with a very quick introduction to data denoising and matrix estimation. So what is denoising? It's the estimate of a fixed, or at least locally in time fixed signal out of noisy estimations. So we have an observation at times t, which is the signal plus a noise t. Usually we can use what we call the law of large numbers to obtain the signal out of an average of over the observations. Matrix estimations is the same when the signal is a matrix. So in small dimensions, it goes as classical estimation. The error in each entry of an average over the time of observations, when the observations are matrices, is small for each entry, and so if the dimension is small, then the total error is small. In large dimensions, something we usually don't have. So, but in fact, this condition is a bit too demanding. It has been proved by Goodelsson and Vershinin that as soon as t is much larger than the dimension, so if the size of the sample is much larger than the dimension of the observations, then this estimation should, under sub-Gaussian hypothesis, work well. However, usually the number of samples or the size of the time window on which we can expect the signal to be stationary is not large, very large. when compared to the size of the vector. So we cannot use this formula. So here is an illustration. So here is the spectrum of this estimator of the covariance matrix when t is only 10 times smaller than larger than n. It's already something, but you see it's not enough. So here is a case where x is a white noise. So the true eigenvalues of its covariance are all equal to 1, and what you get only at the eigenvalues level, not speaking of error on eigenvectors, from this is of course not equal to not close to 1, because it goes from 0.5 to about 1.7. Okay, that's some, you might recognize the Martian Kopasto spectrum. Here is a case where so that's the same experiment, but in a case where x is not a white noise, you have a distribution of eigenvalues for the true covariance matrix, which is not a Dirac mass at 1, and you see that you keep something of that by observation of the empirical covariance matrix, but but with a significative error, and that's only for eigenvalues, not for eigenvectors. And here t is already 10 times, is still 10 times larger than n. When it's only 2 times larger than n, the error in this case is still bigger, and in this case also. Okay, so that's for the limits of this. That's for the problems with this approximation of the covariance matrix of X. So in practice, if we use the covariance matrix of a signal as a measure of risks associated to, for example, to certain positions on the market, this approximation leads to overestimation of the risks associated to larger modes here, because this number is larger than that, and underestimation of risks associated to positions associated to smallest modes here, because this number is way smaller than that one. Okay, so what is cross-covariance matrix estimation? So in this case, we don't consider only one signal, but two signals which can have different dimensions, which might be correlated, and for which at various times we have observations. So we suppose that we have at disposal a sample of observations of the pair x, y. Okay. What we want to estimate now is not the covariance matrix of X, not the covariance matrix of Y, but the cross-covariance matrix of the pair XY. That's the n by p matrix whose ijth entry is a covariance of entry I of X with entry j of Y. So that's the upper right corner of the n plus p by n plus p matrix of the covariance of the signal x and y put together. As before, we can use the law of large numbers, which gives us a first estimator of this cross-covariance matrix, but as above, if n and p are not small, the same kind of problems can occur. So here are illustrations. So here I plotted the singular values of this estimator of the cross-covariance matrix of x and y in the under the null hypothesis, in the null model, where x and y are independent, hence all singular values of this matrix are 0. Here you see that the empirical singular values are not equal to 0. And this number has to be compared to 1 because what we suppose here, because in this case x and y are white noises with covariance matrix having all its eigenvalues equal to 1. In this case, T is 10 times larger than N and 10 times larger than P. Here it's not the null case. Again, X and Y are white noises, but they are supposed to be correlated, which means that this matrix has non-zero singular values. The histogram of the singular values is represented here, and what you see here is a distribution of the empirical singular values, the singular values of this empirical estimator, and you see that it's again you have a significative error. When you pass to n only t only 2 times larger than n, then the error gets still way larger. What you see here is something surprising. The signal x and y have theoretical have theoretical covariance matrices which are both the identity. So the entries both all have variance 1, whereas the cross covariance. So if you think about Cauchy-Schwarz inequality, in theory, all entries of the cross-covariance, all singular values of the cross-covariance matrix should be smaller than 1. That's the case for the true entries of the singular values of the cross-covariance, of the true singular values of the cross-covariance matrix. But as far as the empirical version is concerned, you have some singular values that are larger than 1, even larger than 2. The practical consequences. So before I said that the covariance matrix can be used to measure risk associated to certain positions. The cross-covariance matrix is usually used to detect combinations of the entries of X and of the entries of Y, which have very large or very small correlations. And what we see here is that if we consider the singular values and vectors associated to this part of the singular spectrum, we overestimate the correlation, whereas if we consider singular linear combination associated to this part of the singular spectrum, we underestimate the true correlations. So the conclusion is that the empirical estimator is inefficient in certain situations. There are some estimation techniques that have been developed. The first, regularization. It works, that have been developed, for example, by Bose and co-authors. It works, it can work for structured covariance matrices, for example, the case of band matrices, and especially for this kind of models, which does not correspond to all practical situations. You have the shrinkage, where what you do is average the empirical estimate I used before with a guess of the true value of the covariance or cross-covariance matrix. But you need to have such a guess. The clipping is a technique where you turn all but few eigenvalues, usually the largest one, which are supposed to correspond to signal, whereas the other one would correspond to noise, a constant value which is chosen such that a certain quantity like the trace is preserved. You also have, and that's what I'm going to talk about now, the cleaning, where you look at the eigenvalues or at the singular values if you consider cross-covariance matrices, and change them thanks to some formulas, which in certain cases can if you don't also change eigenvectors or the singular vectors, improve the estimator. So the hypotheses we have in certain, we implicitly make in certain, when using some of the techniques I mentioned in the previous slides, is isotropy. So one common feature of shrinkage, clipping, and cleaning is that the eigenvectors, or the singular vectors, we consider cross-covariance matrices, are unchanged. It means that this estimation technique is agnostic on the directions of the largest or smallest risks, or the largest and smallest correlations of the variables you consider. In fact, what there's behind is a model, a Bayesian model, which is rotationally invariant. It means that you have a prior on the true covariance or of the true cross covariance, whose distribution is invariant under certain actions. So for when it's covariance is the action of the orthogonal group by conjugation. When it's cross covariance, if you don't change the singular vectors, it in a certain way means that you have a prior on the distribution of the true cross covariance, which is invariant on the both left and right multiplication by orthogonal matrices. That's an isotropy hypothesis, a hypothesis of equal possibilities for all directions, usually or equal likelihood. Usually market eigenvectors are not isotropic, so I mentioned markets because I'm working since last summer in a hedge fund where we use this kind of techniques for investment purposes, and where what we work with are covariance or cross-covariance matrices of returns of assets on the market. So this is a plot of measures over time of how isotropic the eigenvectors of the covariance matrices of the returns of a certain market are. So that's the first eigenvector, second, and so on. So I will not go into all details about that, but it's just a way that, especially when you consider the eigenvector associated to the largest eigenvalue, so that's a t-stat, so that's something which should be small. If you had isotropy, it's far from being small. So we don't have isotropy. We should, so ideally also clean the eigenvectors, not only the eigenvalues. The problem is that we don't know how to do that. So what is this cleaning of the eigenvalues or of the singular values I just mentioned? It's what is behind rotationally invariant estimators, RIE. So we have two estimation problems here. The estimation of the true covariance matrix of a signal X out of its empirical covariance computed out of capital T observations of X, or the other problem I mentioned is the estimation of the true cross-covariance matrix of a pair X, Y of signals out of the estimator given by the observation of capital T independent observations of X, Y. And the constraints, so what we want to do in setting up rotationally invariant estimators is to be agnostic on the directions, which means that we want to estimate either the covariance matrix of X or the cross-covariance matrix of XY without changing, in this case, the eigenvectors of this estimator, in this case the singular vectors of this estimator. And we are seeking for an optimal rotationally invariant estimator, which means that given this constraint, we would like to realize the minimum distance to the target, which is in this case the true covariance matrix of X, in this case the true covariance matrix of the pair XY, true cross-covariance matrix. And there's a surprise, both of these problems have a computable solution. What I mean by computable, it is a solution which you can compute simply out of the observation of the x of t's and in this case, and the x of t, y of t's in this case. So for this problem, for the covariance matrix, it is due to some work by Ledoir and Péché with some improvements, some recent improvements. And as far as cross-covariance matrix is concerned, so for this problem, it is due to a joint work with Bouchot and Potters from last year. So the starting point in the first problem of covariance estimation is the following estimator. So that's the empirical estimator of the covariance matrix of X. What you do is computing its spectral decomposition. So you have some eigenvalues lambda k and some eigenvectors uk. Okay, so that's a column eigenvector, and that's its transpose. And what you would like to define would be a cleaned version of this estimator where you don't change the eigenvectors, but you change the eigenvalues in such a way that among all estimators of the true covariance which share this property, which have the eigenvectors of the empirical estimator, so the optimality would be to find the cleaning of the eigenvalues, which among all possible cleaning only of the eigenvalues, not of the eigenvectors, would give the solution which is the closest to the true covariance matrix, so the closest in the sense of the Frobenius norm. What is the Frobenius norm? It's a neutral norm on Hermitian on symmetric matrices. You just take the square root of the sum of the squared entries. It's easy to see that this condition translates, we write that way. The cleaned version of the eigenvalues are given by the quadratic form defined by the true covariance matrix applied to the eigenvectors of the empirical covariance matrix. So I will detail the proof of that in the case of the analog of this formula in the case of cross-covariance matrices a bit later. That's not hard to see. So when cross-covariance matrices are concerned, in the same way, we have an empirical estimator defined just thanks to observations. We consider its singular values decomposition, it's SVD, so it has singular values, left singular vectors, right singular vectors, these are column vectors, and what we would like to define would be an estimator where we just clean these numbers and keep these vectors unchanged, and we would like it to be optimal, which means that as far as only cleaning these numbers is concerned, we would like to be the closest as possible from the Frobenius norm point of view to the true cross-covariance matrix of xy. And it's easy to see that it amounts to choose the cleaned singular values equal to given by this formula. So you take the true cross-covariance matrix of x and y, you multiply it on the right by this vector, on the left by this vector. It gives a number, and that's the optimal cleaned singular values. The problem with both of these solutions is that they involve the eigenvectors of something you can observe, or the singular vectors of something you can observe. So that's okay. We have these vectors at disposal, but also the true covariance matrix or the true cross-covariance matrix, which is of course something we don't know. That's precisely what we want to estimate. So we cannot simply rely on these formulas to define the estimator. So the random matrix theory will provide tools to overcome these difficulties. So what are the formulas for? So we have these it's very simple to see to obtain these formulas. What is harder is then to obtain estimations for these numbers, and they are given by the formulas I will present now. So they involve complex analysis and Stieltjes transforms. So as far as covariance matrices are concerned, let me introduce this function. So the Stieltjes transform of the empirical spectral distribution of the empirical covariance matrix. So these are the eigenvalues of the empirical estimator, and that's a complex number. The cleaned eigenvalues, so the numbers, these numbers are well estimated in the large dimensional limit by the following formula. So you take the empirical versions and you divide it by this number, so that this involves it involves this function very close to the real line, and it works well. As far as cross-covariance matrices are concerned, you still work with you still start with the singular value you want to clean, and you have also to apply it a factor, which is given by some more complicated formulas, also involving complex analysis, which I will not detail here. So for both of these RIEs, so rotationally invariant estimators, perform way better than the naive estimators, and models, of course, with good isometry, isotropy, not isometry property. What I mean by isotropy is that they are defined thanks to a model where the true covariance matrix or true cross-covariance matrix is chosen at random with a certain invariance under the action of the orthogonal group. So here is a plot. So for the cross-covariance, so that's a new model where x and y are both Gaussian white noises, and where they are independent. So the true cross-covariance matrix of x and y is 0, and here is a plot of the cleaned version of the singular values versus the singular values we have observed on the empirical estimator. So you see that these singular values go up to 1.5, whereas the cleaned version, thanks to the formula I partly presented before, is much smaller. Okay, so this number has to be compared to that, and all of this has to be considered in the scale 1, because x and y have eigenvalues. X and y have covariance matrices. Have all entries of x and y have variance 1. Okay, so that's for the null model. I also before presented a graph where x and y. So that's a follow-up of the graph I presented before. So in this case, x and y are still both white noise, but they have correlations. In this case, that's not true anymore. The cross-covariance matrix of x and y has some non-zero singular values. They are represented here with this. So that's their histogram in red. In blue, you have in black you have the histogram of the singular values of the empirical estimator, and in red you have what you obtain after the cleaning procedure. Okay, so you see something surprising here. So you have the true singular values in red, the empirical the empirical version, if you want. So that's the singular values of the empirical estimator. I told before that the larger singular values are larger than the theoretical values, and the smallest empirical ones are smaller than the theoretical values, than the theoretical smallest one. What you would imagine would be that an estimator tries to get the closer to this, but will stay between that and that. And that's not the case. What you observe is that the estimator goes way below this bound. So that's something I will discuss a bit here. So another way to say that is to in statistics we say that it's not a converging estimator. So question: will the optimality I presented before means that the cleaned singular values will be close in the large dimension limit to the true ones? So that would mean that the blue curve is close to the red curve. So of course that will be true if t, the number of samples we have at disposal, is way larger than the dimension. But if it's not the case, optimality will not imply that. What it will imply is that on average the clean singular values are smaller than the true ones, which are on average smaller than the empirical versions. Precisely, we have the following formulas. So this formula says that the empirical singular values are larger than the true ones because they are equal on average to the true ones plus something which is larger than 1 plus something which is positive. And on average, the clean singular values times the non-cleaned empirical ones are equal to the true ones to the square, which means, given that this is on average larger than that this will be smaller than that. How come an optimal estimator can present such a bias? The reason is that it's optimal as a matrix estimator, not as an estimator of the singular values. And given, and so it's optimal as a matrix estimator. It knows that the observation on the estimation on the eigenvectors or on the singular vectors is noisy. So to be optimal at the matrix level, it has to shrink the weight given to these singular vectors and clean the singular values up to some values which are below the true ones. Okay? In other words, if you're absolutely not sure of the singular vectors and don't want to do a too big mistake, then weight them with some small weights. That's what happens, and so that's for cross-covariance matrices, but the same kind of bias appears for the optimal rotationally invariant estimator for covariance matrices. Okay, so let me now pass to proofs or sketch of proofs. So how can we translate the optimality condition? So we have an empirical estimator, which is given by the average of the sample we have at disposal of this one-time estimator of the cross-covariance matrix. We perform its SVD, so these are the singular values and these are the singular vectors, and we would like to clean these singular values in such a way, in an optimal way, which means that we want the distance from the cleaned version of this estimator to the true cross-covariance matrix to be minimal in Frobenius norm. This can be so this we write that way, that the diagonal matrix of the cleaned singular values multiplied on the left by the matrix whose columns are these singular vectors, and on the right by the transpose of the matrix whose columns are these right singular vectors. Okay, and we want it to be minimal in Frobenius norm. The Frobenius norm is invariant on the left and right multiplication by orthogonal matrices. So we can multiply it on the left by the inverse of this matrix, on the right by the inverse of this matrix, at least when n and p are equal. Because that's so when n is not equal to p, when that's a rectangular matrix, you have this little problem that so for example, if you have more columns than rows, then the right singular vectors will not define the basis. It will only define an orthonormal system. But that's not a real problem. We can turn this condition to that one. So we have only multiplied on the left by the inverse, which is its adjoint of this matrix, and on the right by the inverse of this matrix, and use the fact that these operations do not change the Frobenius norm. And what we get is that we want these numbers to be such that the distance of this diagonal matrix to that one has to be minimal in Frobenius norm. But now it's very easy. You have a diagonal matrix, another matrix. You want the Frobenius norm of the difference between both to be minimal. What you need is simply to have these the numbers on the diagonal to be equal to the diagonal entries of this matrix. So you have the cleaned version of the case singular value, which is equal to the case entry of this matrix, which rewrites this true cross-covariance matrix times Vk on the right and Uk star on the left. So that's how we arrive to the simple formula I presented above. So we have to estimate this number. Again, the problem is that these vectors are vectors we can observe because they are we can compute this SVD. However, this matrix is something we don't observe, which is precisely what we want to estimate. So we have to estimate this, and that's not easy. So that's the main difficulty of this work. So how will we estimate this? So let me introduce two objects which are measures. So that's the singular values distribution of the empirical estimator. So these are the empirical singular values. Okay, before the cleaning. So you symmetrize this distribution. You also consider the opposites of the number, and you take the empirical distribution, the uniform distribution, and then you take the same measure with some weights. So you put a minus here, and more important, you multiply this by this mysterious number we want to estimate. Okay, and what we get is that these numbers that we want to estimate are simply the Radon-Nikodym derivative of this measure with respect to that one. So that's nothing here. But writing things that way, if you at least on the informal level divide this and that by dx by the Lebesgue measure, what you get is the derivative of this measure, the density of this measure divided by the density of this measure. So of course it doesn't make sense because these measures do not have sense, but they do not have densities. But you can give it a sense using Stieltjes transform. So you know that if a measure has a density, then its density is the imaginary part of, not the Stieltjes transform, the imaginary part of the Stieltjes transform on the real line, and so this expresses as a ratio of imaginary parts. I should have added this of Stieltjes transform. So what you need. So this is just a way to say that these numbers, at least when you average them on intervals, can be estimated as ratios of imaginary parts of Stieltjes transforms. So it's a new way to move the problem to a level where we don't know how to solve them. But so because that's a measure whose Stieltjes transform is of course observable because you just compute the resultant of this matrix and takes its trace. Whereas, as far as that one is concerned, so that's a measure we can define, but we cannot observe. However, the Stieltjes transform of this measure can be expressed in a more sympathical way. So it's very easy. It's 10 lines of computation. You can express the Stieltjes transform of this measure, so that's not a probability measure, but it has a Stieltjes transform, as follows. So you have the resultant of the empirical cross-covariance matrix multiplied by its adjoint. You multiply it by something which is again the empirical cross-covariance matrix. So these are things you can observe. And here again, you have a term you cannot observe. That's the true cross-covariance matrix. So that's again something which we do not observe directly. However, using tools which are quite usual in matrix theory, as Stein formula and concentration of measures. So Stein formula can be used when we suppose that x and y are jointly Gaussian. When you don't suppose that, that's something we did not write completely, but we could use cumulants instead. And that's something you can estimate, and that solves the problem. So the size is the end of line.
Yeah, okay. Thank you very much. So now it's open for questions.
Yeah, I have a question, especially about the estimation of the covariance, so not the cross-covariance. You mentioned a reference, you said that this was a recent...
Could you please speak up?
You mentioned a reference, and you said it was a recent result. Can you just go back to that reference, please? Okay, so long way to go. So while you're going back, okay, so let's sheet with, okay, because there is quite a consistent and massive work done initiated by Javier Mestre of Polytechnica Catalonia, and then followed up by Philippe Loubaton in France, where they actually derive consistent estimators for both eigenvalues and eigenspaces, so also the eigenvectors for the projectors of the eigenspaces. In this regime of large dimension, they call them Kirko estimator, G estimation for these covariances. So, and there you don't have this bias. In fact, you get something that converges very well as n and t go to infinity at the same speed, so they're linear. And you correct both eigenspaces and eigenvalues in a way that is quite similar to this, but it's not exactly the same. And I wonder if there is a relation and what this relation would be.
I know that I know that this work are known by Bouchot and Potters, who worked much on the covariance matrix estimation. It seems to me that in the cases where they are using it, even though, as I said, we should also clean the eigenvectors, they still prefer to use the RIE on the eigenvalues and be agnostic on the eigenvectors. So if I'm not wrong, I think that this work you mentioned was in the framework of what we call robust statistics. Am I right?
Well, the second question is when these things work, right? So for what kind of ensemble these things work? Because I think also here you must have some assumptions on your ensemble, because when you have, for example, that these traces and think of the true covariance converge in some way that you can actually get them from the empirical covariance, there must be some assumption. In their case, in the original Mestre case, the ensemble is essentially random vectors whose covariance is essentially has a bunch of isolated eigenvalues of a certain multiplicity, and the multiplicity is so when the dimension goes to infinity, you have a sort of mass point. So the original eigenvalue distribution is a discrete mass point distribution, and then this was generalized by Loubaton and others for the so-called signal plus noise model, where you have an arbitrary deterministic signal part, which is the outer product of a rank efficient matrix by itself, plus the noise part, which is Gaussian ID or sub-Gaussian ID with a finite 8 moment, this usual regularity conditions.
My feeling is that usually the nature of the distribution of eigenvalues, so you mentioned some Dirac masses, can make some mathematical difficulties, but that usually the key problems are not here. They are in the geometry of eigenvectors. This is proved to be optimal in the very specific setting where you don't want to clean the eigenvectors of the singular vectors, and when will you not want to clean them? You will not want to clean them when you suppose them to be how distributed, uniformly distributed on the orthogonal group. If you observe a uniformly distributed random matrix on the orthogonal group, you cannot estimate it better than just reading what you have observed. Okay, so that's if you suppose, for example, your eigenvectors to be not too far from the canonical basis, or to have a certain block structure or things like that, then you might have some other estimators which work better.
Yeah.
As I told you, this is applied in a context where the eigenvectors are not isotropic, where they might not be uniformly distributed on the orthogonal group. However, we have not found any estimator. So all estimators are based on a prior distribution on the eigenvectors. That one is based on the prior distribution that they are uniformly distributed and independent of the eigenvalues. We have not found in the literature, and I know that Bouchot and Potters know the work you mentioned, any estimation technique which would work better just because of that, because of the priors we implicitly make on the eigenvectors.
Okay. Well, I'm curious to make comparison in cases for which I am interested.
Okay, so one more question, because
Just
we're
so
far
the
behind
bound
time.
is shrinking,
And
right?
then
When
we
you
move to the-
at large, I mean, it should be
What?
shrinking.
to the
The bound should be shrinking, right?
Yeah.
Yeah, that's, I think it's okay.
Well,
It's not biased,
May,
unbiased.
may I ask one question?
Sorry, but
Sorry, a slightly different question. So you're using the Frobenius norm for your risk. I mean, I think at the end of the day, you want to make money with this, and you do certain things with the covariance matrices. Could there be other risks that could be relevant that would lead to slightly different results? I mean,
so using so precisely that we use past assets returns and the empirical covariance to have what we call a risk model, a model for the fluctuations we can expect and the joint correlations of the assets.
okay. So directly this.
So that's purely statistical. You have macroeconomical models which are not based on the. I think it replies to.
okay, so the last question.
I think that the real problem of this type of estimators is that you have to approach this real line, and then if you are too close, then it is too noisy. If you are too far, the result is biased. And well, if you take the result, for example, the 1/4 root of n times t, you don't do this well. So you have to use this something which is called quest by Lenoir and Wolf, which is a perfect solution of this problem, and it stabilizes the result. Actually, and the question is whether you invented something like inverse quest procedure for your case. I mean, when you work with cross-correlation.
I don't know what you are mentioning, but what we do as far as getting close to the real line is concerned is never getting smaller than the average distance between two eigenvalues, because it will of course kill the smoothness, and get just above that. So the average distance, if the average distance is 1 over n.
It works very well in the bar, but if you are close to, well, end of the support, then it has instabilities.
Yeah, so
Perhaps we can move this discussion to the coffee break because we are behind.